Look up at the night sky and tell me what you see. You probably see a calm, static tapestry of ancient stars, frozen in time like a photograph. But that stillness is a terrifying lie, because the fabric of reality is being stretched until it screams, and something is pulling the darkness apart faster than physics should allow. Every second you watch this video, a galaxy somewhere in the deep void crosses a horizon line and vanishes from our view forever, never to be seen again. We used to think the universe was a stable, unchanging island in the void, but we were wrong, and the consequences of that mistake are starting to haunt us. There is a speed limit in our universe, a cosmic law that says nothing can travel faster than light, yet the galaxies are mocking that law right now. Imagine running a race where the finish line is moving away from you faster than you can ever run. That is the fate of every photon trying to reach Earth. This isn't just about distant stars moving away. It is about the space between them, the very vacuum itself, generating more space from absolutely nothing. Astronomers call it dark energy, but that is just a fancy label for a monster we cannot see, cannot touch, and definitely cannot stop. If you measure the expansion rate using the radiation from the Big Bang, you get one number, but if you look at exploding stars, you get a completely different number. This discrepancy is called the Hubble tension, and it is keeping physicists awake at night because it suggests our understanding of reality is fundamentally broken. We are standing on a planet that feels solid, but we are adrift in a violently expanding ocean where the shoreline is receding faster than we can swim. 100 years ago, Edwin Hubble looked through a telescope and realized the Andromeda Galaxy was one of the few things not fleeing from us in terror. Everything else is rushing away, red shifted into oblivion, meaning the light waves are being stretched out until they become invisible to the human eye. The scary part isn't that they are moving. The scary part is that the speed of their retreat is accelerating every single day without pause. In a distant future, the night sky will be completely empty, and human civilizations, if they exist, will believe they are the only galaxy in the entire universe. All evidence of the Big Bang, the cosmic microwave background, and our neighbors will have been erased by this relentless, faster-than-light expansion. We live in a privileged time where we can still see the truth, but the window is closing, and the universe is slowly deleting its own history. Think about the atoms in your body. The space inside them is technically expanding too, but electromagnetic forces and gravity are fighting a war to keep you intact. But what happens if this expansion force gets stronger? What happens if it overpowers gravity, then electromagnetism, and finally, the strong nuclear force? That theoretical nightmare is called the Big Rip, a moment where stars, planets, and even atoms are torn apart by the sheer force of empty space. Physicists are desperately trying to measure the parameter of dark energy to see if we are heading toward a stable freeze or a violent shredding. The James Webb Space Telescope was supposed to solve the Hubble tension, but instead, it just confirmed that the universe is even weirder than we thought. It found galaxies that are too big and too bright for the early universe, suggesting that expansion might have worked differently in the deep past. Some scientists are now whispering about early dark energy, a mysterious surge of power that happened shortly after the Big Bang and then vanished. Others suggest our understanding of gravity itself is flawed, and that general relativity breaks down when we look at the vast scales of the intergalactic void. There is a region in the sky called the Great Attractor, a gravitational anomaly pulling us and thousands of other galaxies toward a certain doom. But even the Great Attractor cannot win against dark energy. Eventually, the expansion will rip us away from its grasp and isolate us in the cold dark. Imagine being on a ship in the middle of the ocean, and suddenly the water starts multiplying, pushing the nearest island thousands of miles away in seconds. That is the situation for the Milky Way. We are becoming cosmic orphans, disconnected from the web of causality that binds the universe together. The scary implication is that there are parts of the universe we can never interact with, entire civilizations that are forever locked behind the event horizon. We call this the cosmic event horizon, a boundary beyond which light can never reach us because the space carrying it is expanding faster than light speed. Every second, that horizon swallows more of the universe, effectively deleting information from reality as if it never existed in the first place. Is space-time a substance? Is it a fluid, or is it a geometric illusion that we are mistaking for a physical object? If the vacuum has energy, and that energy is infinite, then the empty space in a coffee cup has enough power to boil all the Earth's oceans. Quantum field theory predicts this energy should be massive, but if it were, the universe would have ripped itself apart instantly after the Big Bang. This is the cosmological constant problem, the worst prediction in the history of physics, off by a factor of 10, followed by 120 zeros. We are missing something fundamental, a piece of the puzzle that is hidden in the darkness, and our ignorance might be the only thing keeping us sane. Maybe we are living inside a bubble, and the expansion is just the walls of our cage growing larger as something outside blows air into it. Some theorists propose that our universe is colliding with another, and the energy from that impact is what we perceive as this accelerating expansion. The multiverse theory isn't just science fiction. It might be the only way to explain why our vacuum has just the right amount of energy to kill us slowly. If the expansion continues, the sky will go dark, the stars will burn out, and the universe will enter an era known as the heat death. But the data from recent supernovae suggests something even stranger. The expansion isn't smooth, it might be lumpy, creating pockets of chaos. We need to look at the standard candles of the cosmos, the Type 1a supernovae, which explode with such precision they act as cosmic yardsticks. When we measure them, they are dimmer than they should be, whispering to us that they are further away than our old physics could ever explain. This realization won the Nobel Prize, but it also broke the hearts of scientists who wanted a simple, elegant, and static universe to live in. Now we face the ultimate question. Will the universe expand forever, or will it snap back in a big crunch, destroying everything in fire? Or will it rip? A violent end where the fabric of space-time itself fails, and the laws of physics dissolve into absolute nothingness? To find the answer, we have to leave our comfort zone and look at the invisible forces that dictate the geometry of our reality. We are about to dive into the impossible numbers, the broken theories, and the terrifying vastness of a cosmos that is running away from us. Buckle up, because the further we go, the faster the light fades, and we are venturing into the dark heart of the expansion problem. To understand why the sky is running away from us, we have to go back to a time when we thought the heavens were eternal and unmoving. Albert Einstein, the architect of modern gravity, looked at his own equations and saw a monster that terrified him. His general relativity predicted that a universe full of matter should be unstable. Gravity is an attractive force, so, logically, everything should be pulling together, collapsing into a singular point of crunching doom. To save the universe from this theoretical collapse, Einstein invented a ghost, a fudge factor he called the cosmological constant. It was a mathematical repulsive force designed solely to hold back the crush of gravity and keep the universe static, safe, and boring. He created a counterforce to gravity, a scaffold to hold the stars in place, unaware that he was suppressing the truth of a dynamic, violent cosmos that refuses to sit still for our comfort. But the universe does not care about the comfort of physicists or the elegance of their equations. In the 1920s, Edwin Hubble peered through the Hooker telescope at Mount Wilson and shattered Einstein's static illusion into a billion pieces. He looked at the light coming from distant galaxies and noticed something impossible. The light was redder than it should be. This is the Doppler effect on a cosmic scale. Just as a siren sounds lower pitch as it drives away from you, the light from galaxies stretches into the red part of the spectrum as they flee from Earth. Hubble realized that the universe wasn't standing still. It was exploding outward. Every galaxy was rushing away from every other galaxy, implying that yesterday they were closer, and the day before that even closer, pointing back to a single moment of creation that we now call the Big Bang. When Einstein heard the news, he reportedly called the cosmological constant his greatest blunder, discarding it like a piece of trash math. He thought he had failed by not predicting the expansion, but the irony is that his blunder was actually a prophecy waiting to be fulfilled. For decades, we assumed the expansion was a simple inertial event. An explosion happens, things fly apart, and then gravity slowly pulls them back. We thought the universe was like a ball thrown into the air. It goes up, slows down, and eventually falls back down. We were convinced that gravity was the dominant force in the cosmos and that eventually the expansion would decelerate. We believed we were living in a slowing universe, one that would eventually stop and crunch back together. But we were dead wrong. The ball isn't slowing down. The ball has grown wings and is flying into the sun. To understand the horror of what is happening now, you have to look at what exists between the stars, the vacuum. For centuries, we thought a vacuum was just emptiness, a void where nothing exists, but quantum mechanics revealed that nothing is actually very heavy. The vacuum is a seething, boiling sea of virtual particles appearing and disappearing in zeptoseconds. Pairs of matter and antimatter pop into existence, borrow energy from the void, annihilate each other, and return the energy. This constant bubbling creates a pressure, an energy density inherent to space itself. If you calculate how much energy should be in the empty space inside a simple coffee cup based on quantum field theory, the result is enough to boil all the oceans on Earth instantly. Space is not empty. It is alive with potential power. This leads us to the most embarrassing number in the history of science, a discrepancy so large it feels like a cosmic joke. If you take the theoretical energy of the quantum vacuum, the energy that should be pushing space apart, and compare it to the expansion we actually observe, the numbers do not match. They don't just disagree, they are from different realities. The theoretical prediction is 120 orders of magnitude larger than what we see. That is a 1 followed by 120 zeros. It is the worst prediction in physics, known as the vacuum catastrophe. If the quantum theories were fully correct, the universe should have ripped itself apart in a fraction of a second after the Big Bang. We shouldn't be here. The fact that we exist means something is canceling out that energy, or we are fundamentally misunderstanding the nature of nothingness. So we were left with a mystery. We knew the universe was expanding, we knew the vacuum had energy, but we assumed gravity was winning the war. Then came 1998, the year our picture of the universe turned into a nightmare. Two independent teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure how much the universe was slowing down. They looked at Type Ia supernovae, exploding white dwarf stars that burn with a specific brightness. By measuring how dim these explosions were, they could calculate how far away they were and how fast they were moving. They expected to see the data curve downward, showing that gravity was breaking the expansion. They were looking for a deceleration. They were looking for the safety of a dying momentum. Imagine stepping onto the brakes of your car to avoid a cliff, but instead of slowing down, the car suddenly accelerates to top speed. That is exactly what the astronomers found. The supernovae were fainter than they should have been, which meant they were much further away than the math predicted. The expansion wasn't slowing down, it was speeding up. Something was hitting the cosmic gas pedal. The data was so shocking that both teams thought they had made a mistake. They checked their telescopes, their code, their math, but the universe wasn't lying. About 5 billion years ago, a switch flipped in the cosmos. Gravity lost its grip, and a mysterious repulsive force took over, pushing galaxies apart with exponential power. We had discovered dark energy, and we had no idea what it was. This discovery resurrected Einstein's blunder. The cosmological constant was back, but now it wasn't a shield to keep the universe static. It was the engine of our isolation. We now believe that dark energy makes up roughly 68% of the total energy in the universe. Think about that. Everything you have ever seen, every star, planet, gas cloud, atom, and person makes up less than 5% of the universe. Dark matter makes up about 27%. The rest, the vast majority of reality, is this invisible, expanding force that we cannot touch or see. We are drifting on a tiny raft of matter in a vast ocean of dark energy that is growing larger by the second. We are the minority. We are the anomaly in a universe made mostly of repulsive void. The implications of an accelerating universe are profoundly disturbing because it introduces the concept of the cosmic event horizon. In a decelerating universe, light from distant objects would eventually catch up to us, no matter how far away they were. We would eventually see everything. But in an accelerating universe, there is a limit. There are galaxies emitting light right now that will never reach us. The space between us and them is expanding faster than the speed of light. They are retreating faster than their photons can swim. They are falling off the edge of the observable universe. Every day, we lose contact with huge sections of the cosmos. The universe is effectively deleting files from its hard drive, and we can never recover them. This isolation creates a paradox for future civilizations. Imagine a civilization arising 100 billion years from now. By then, all the other galaxies will have accelerated beyond the horizon. Their night sky will be empty save for the stars within their own merged galaxy. They will look out and see a static, dark void. They will have no way of knowing the Big Bang happened. They will have no evidence of the expansion. They will construct perfectly valid theories of physics that say they are alone in a static universe. And they will be wrong. We live in a golden age of cosmology simply because we can still see the evidence of our origins before the universe hides it forever. We are the witnesses to a crime scene that is being actively scrubbed clean. But what is dark energy? This is where the theories turn from scientific to existential horror. One possibility is that it is an intrinsic property of space itself. As space expands, more vacuum is created. If the vacuum has energy, then more space means more energy, which causes more expansion, which creates more space. A runaway feedback loop of creation. This means the universe is a perpetual motion machine of nothingness, generating infinite energy from the void. It suggests that empty space is the most potent substance in existence, a relentless fluid that wants to dilute matter until it is effectively non-existent. It treats galaxies like impurities in a crystal, pushing them out to the edges to create a perfect, featureless void. Another theory, perhaps even more unsettling, is that dark energy is a field, a fluid-like substance that permeates the universe, which physicists call quintessence. Unlike the cosmological constant, which is static, quintessence can change over time. It can get stronger or weaker. If it gets weaker, the universe might eventually stop expanding and collapse. But if it gets stronger, that leads to the phantom energy scenario. If the density of dark energy increases with time, it won't just push galaxies apart. It will eventually overcome the gravity holding the Milky Way together. Then it will overpower the gravity holding the solar system together. The Earth would be ripped away from the Sun. Then, in the final moments, it would overcome the electromagnetic and nuclear forces, ripping atoms apart. This is the Big Rip scenario. In this model, the universe has a distinct expiration date. A countdown clock is ticking, but we can't see the display. As the phantom energy rises, the horizon of the observable universe shrinks. The edge of the universe closes in on us. First, the distant stars vanish. Then the planets in our solar system disappear into the black. Then the moon is ripped away. Finally, the horizon becomes smaller than an atom, and all structure in the universe is torn asunder. It is the ultimate vaporization of reality, leaving nothing but a singular, chaotic soup of unbound particles that can never interact again. It is a death more absolute than silence. But let's return to the here and now, where the Hubble tension is making scientists question reality. We measure the expansion rate in two main ways. One is by looking at the baby picture of the universe, the cosmic microwave background, CMB. This is the afterglow of the Big Bang. The European Space Agency's Planck satellite measured this ancient light with incredible precision. Based on the physics of the early universe, Planck predicts an expansion rate of about 67 kilometers per second per megaparsec. It is a solid, robust prediction based on the standard model of cosmology. It is the expect value. It tells us how the movie should end based on the opening scene. The second method is to look at the adult universe, measuring the distances to pulsating stars called Cepheids and Type Ia supernovae in nearby galaxies. This is what the Hubble Space Telescope does best. When astronomers measure the local universe, they get a value of about 73 or 74 kilometers per second per megaparsec. 67 and 74 are not the same number. The error bars do not overlap. This is a 5 sigma statistical significance, which in science speak means this is not a fluke. It means either our measurements are wrong, which seems unlikely after decades of checking, or our fundamental understanding of the universe is broken. The universe is expanding faster now than it should be based on its past. This discrepancy suggests that something happened between the beginning of time and now that we didn't account for. Maybe there was a burst of early dark energy that gave the cosmos a kick in its infancy. Or maybe we are living in a vast cosmic void, a localized bubble of emptiness that is expanding faster than the denser regions outside. If we are inside a billion light-year-wide bubble, our measurements would be skewed, making it look like the whole universe is accelerating more than it is. We would be like fish in a bowl thinking the whole ocean is curved glass. It forces us to ask, is our corner of the universe special, or is it a trap? The crisis is deepening with every new telescope we launch. The James Webb Space Telescope was hoped to resolve this tension, perhaps finding that the Cepheid stars were being measured incorrectly due to dust or crowding. But early data from Webb seems to confirm the Hubble measurements. The tension is real. The universe is acting strangely. It is almost as if the laws of physics are changing over time, or as if gravity behaves differently on massive scales. Some theorists are proposing modified gravity theories, suggesting that Einstein's general relativity is just an approximation that fails when you look at the vast emptiness between galaxy clusters. We might be using a ruler made of rubber to measure a room that is stretching. Consider the fine-tuning problem. The amount of dark energy is incredibly small compared to what quantum theory predicts, but it is also incredibly precise. If there were slightly more dark energy, the universe would have expanded so fast that galaxies would never have formed, stars would never have ignited, we would not exist. If there were slightly less, the universe would have collapsed back into a big crunch billions of years ago. We seem to exist on a razor's edge, a statistically impossible sweet spot that allows for life. This leads some to the anthropic principle. We observe these values because if they were different, we wouldn't be here to observe them. But that isn't an explanation, it's a surrender. The multiverse theory offers a dark solution to the fine-tuning problem. Perhaps there are infinite bubble universes, each with a different value for dark energy. Most of them are dead, either ripped apart instantly or crushed into singularities. We just happen to inhabit one of the rare, survivable bubbles. In this view, our universe isn't a grand design. It's a winning lottery ticket in a sea of cosmic corpses. We are the survivors of a multiverse selection process that eliminates 99.999% of all potential realities. It makes our existence feel less like a miracle and more like a statistical accident in a graveyard of failed universes. But what if the expansion isn't driving us apart? What if it is pulling us towards something? This is the dark flow hypothesis. When we map the movement of galaxy clusters, we see a strange, coherent motion that can't be explained by the distribution of matter we see. It looks like huge chunks of the universe are drifting toward a specific point, beyond the observable horizon. It is as if something massive, something bigger than our entire observable universe, is tilting the table, causing galaxies to slide into the dark. Are we being sucked into a drain? Or is there a megastructure outside our visual range that dwarfs everything we know? Let's talk about the Great Attractor again, but with the context of dark energy. The Great Attractor is a gravitational anomaly in the direction of the constellation Centaurus. It is a mass concentration equivalent to tens of thousands of galaxies, pulling the Milky Way and our local supercluster, Laniakea, towards it at 600 kilometers per second. We are hurtling towards this gravitational monster, but we will never reach it. Dark energy is the tragedy of this story. We are running a race towards a finish line that is being pulled away faster than we can run. The expansion will eventually overpower the pull of the Great Attractor, and the structure we are destined to join will be torn from our grasp. We are destined to be alone. There is a theory called vacuum decay that adds another layer of terror to the expansion. We assume the vacuum of space is in its lowest energy state, the true vacuum. But what if we are in a false vacuum? Think of a ball resting in a small valley on a mountainside. It seems stable, but there is a deeper valley further down. If something kicks the ball, a high-energy quantum event, it could roll down to the true bottom. In physics, this would be a bubble of true vacuum, expanding at the speed of light. Inside this bubble, the laws of physics would be rewritten, chemistry would fail, matter would dissolve. If such a bubble started a billion light-years away, we wouldn't see it coming. It would hit us instantly, and we would simply cease to exist. The expansion might be stretching the fabric of space so thin that it risks triggering this catastrophe. As the universe expands, the temperature of the cosmic microwave background drops. Right now, space is about 2.7 Kelvin, just above absolute zero. As expansion continues, this temperature will approach zero. The universe is slowly freezing. But in a weird twist, the temperature of the dark energy horizon, the radiation emitted by the cosmological horizon itself, might become relevant. This is Hawking radiation applied to the universe's edge. We are living inside an inverted black hole, In a black hole, you can't get out. In our universe, things can't get in from beyond the horizon. We are trapped in a thermal enclosure that is slowly expanding, dissipating all heat until entropy reaches its maximum. This is the heat death, the state of maximum disorder where no energy can be transferred and no life can exist. The concept of time itself begins to break down in an accelerating universe. If the expansion continues forever, the universe will enter an era where time loses its meaning. With no events, no collisions, and no light interacting with matter, there is no clock to measure the passage of time. Protons might eventually decay, leaving only a soup of photons and leptons. In this dark era, the universe becomes a timeless void. It will exist for eternity, but eternity is meaningless when nothing changes. We are racing towards a state of eternal stasis, a frozen snapshot of nothingness that lasts forever. It is the ultimate end of history. Some scientists, desperate to avoid this bleak ending, propose cyclic models. Roger Penrose's conformal cyclic cosmology suggests that the end of one universe is the Big Bang of the next. In the far future, when only photons remain, scale becomes irrelevant. A universe the size of a proton and a universe of infinite size look mathematically identical if there is no mass to provide a reference. In this geometric trick, the infinite expansion of our eon becomes the singularity of the next. We might be living in the aftermath of a previous universe's heat death. The expansion we fear might be the gestation period of the next reality. It is a beautiful thought, but it implies an endless cycle of birth, suffering, and erasure. Let's look closer at the voids, the vast empty spaces between galaxy filaments. The Boots void is a sphere of nothingness 330 million light-years across. If the Milky Way were in the center of the Boots void, we wouldn't have known other galaxies existed until the 1960s. These voids are the crystal balls of our future. They are regions where dark energy has already won. They are expanding faster than the denser regions, squeezing the galaxy filaments into thin strands. The universe is becoming a cosmic web of tenuous threads surrounding massive, growing bubbles of emptiness. We live on one of those threads, and the bubbles are pushing against us, trying to snap the line. We often visualize the expansion as stars moving away, but it is more accurate to say the grid is expanding. Imagine drawing a grid on a rubber sheet and placing coins on the intersections. As you stretch the sheet, the coins don't move across the rubber. The rubber between them grows. This means the galaxies aren't traveling through space in the traditional sense. They are riding the expansion. This allows them to recede faster than light without violating relativity, because it is space itself that is expanding, and space has no speed limit. The speed of light limit applies to things in space, not space itself. This loophole is what allows the universe to disconnect itself, creating pockets of reality that are causally separated forever. What happens to information in an accelerating universe? Physics tells us that information is never destroyed. The quantum state of a particle is preserved. But the cosmic event horizon challenges this. If a galaxy passes beyond the horizon, its information is lost to us. Does it still exist? Is it stored on the surface of the horizon like a hologram? This parallels the black hole information paradox. We might be living in a universe that leaks information into the void. If reality is defined by what can be measured, and we are losing the ability to measure the vast majority of the universe, is the universe becoming less real over time? Are we dissolving into a lower resolution simulation? There is a fringe possibility that dark energy isn't real at all, but an illusion caused by inhomogeneous cosmology. We assume the universe is the same everywhere, homogeneous and isotropic. But what if we are in a region with less matter than average? Gravity would be weaker here, so the expansion would look faster compared to the denser outside. It's a long shot, but it highlights how much of our knowledge is based on assumptions. We assume the Copernican principle that we are not special. But if we are in a special, empty place, our entire model of the cosmos is a hallucination caused by our local geography. We might be misinterpreting the geometry of the universe because we can't see the whole shape. Let's consider the big freeze versus the big rip again. The critical value is the equation of state parameter, W. If W equals -1, we get a steady acceleration and a lonely freeze. If W is less than -1, like -1.5, the phantom energy grows, and we get the rip. Current measurements put W very close to -1, about -1.03 with an error margin. That tiny margin is the difference between an eternal, lonely graveyard and a violent, shredding apocalypse. We are balancing on a knife edge between two horrors. Future missions like the Euclid telescope are designed specifically to nail down this number. We are building machines to tell us exactly how we are going to die. There is something deeply unsettling about the fact that the universe became dark energy dominated only recently in cosmic history. For the first 9 billion years, gravity was the boss. The expansion was slowing. Then, as matter spread out and diluted, the constant density of dark energy took over. It's like a sleeper agent that waited for the galaxy to weaken before striking. This transition era, the cosmic jerk, happened roughly when our solar system was forming. It is a chilling coincidence. Just as life was beginning to stir on Earth, the universe decided to start tearing itself apart. We are children of the acceleration, born in the era of the Great Disconnect. If you look at the structure of the universe on the largest scales, it looks like a neural network, a brain. The distribution of dark matter in galaxies mimics the connections of neurons. Some ask, is the universe conscious? If it is, then the expansion is a lobotomy. As galaxies are pushed out of causal contact, the connections are severed. The brain is being pulled apart, preventing signals from crossing from one side to the other. An accelerating universe is a dying mind, losing its ability to think, process, or remember. We are witnessing the onset of cosmic dementia, where the different parts of the whole can no longer communicate. Technology can't save us from this. Even if we invent warp drives or travel at 99% the speed of light, we can never catch a galaxy that has crossed the horizon. It is physically impossible. The space is being created faster than we can traverse it. We are trapped in our local group of galaxies, the Milky Way, Andromeda, and a few dozen dwarfs. This is our permanent prison cell. In 1 trillion years, these will merge into one giant elliptical galaxy. Let's call it Milkdromeda, and that will be the entire observable universe for its inhabitants. They will have no idea that trillions of other galaxies once existed. We are the last generation to know the true scale of the cosmos. The light from the Big Bang, the cosmic microwave background, is also being stretched. Right now, it is microwave radiation. Eventually, it will be stretched into radio waves with wavelengths larger than the observable universe. It will become undetectable. The afterglow of creation will fade to total black. When that happens, the evidence for the Big Bang will be gone. Future scientists will have no way to construct a standard model. They will be cosmic archaeologists with no fossils to study. They will live in an ahistorical universe, cut off from their own past by the stretching of space-time. We struggle to visualize 4D space-time expanding. Imagine a balloon with ants on it. As you inflate the balloon, the ants move apart, but the universe has no outside to expand into. It creates its own outside. It is expanding into itself. This self-generating geometry is what makes the math so difficult. It defies human intuition. We evolved to understand distance as a fixed thing. A valley is a valley. But in the cosmos, the valley stretches while you walk it. The mountain moves away while you climb it. We are creatures of static geometry trying to comprehend a dynamic, fluid reality. Let's go back to the vacuum. The Casimir effect proves that the vacuum has pressure. If you put two metal plates very close together in a vacuum, they are pushed together. Why? Because only certain wavelengths of virtual particles can fit between the plates, while all wavelengths fit outside. The external pressure is higher. This proves the sea of energy is real. We are swimming in it. The problem is that this sea is pushing the universe apart. We are drowning in an ocean of energy that we can't harvest, can't stop, and can barely understand. It is the ultimate resource, yet it is the agent of our doom. What if dark energy interacts with dark matter? We usually treat them as separate. Dark matter pulls, dark energy pushes. But if they are coupled? If dark matter decays into dark energy over time, the acceleration will get worse. This would solve the why now problem. Maybe the universe ran out of glue, dark matter, and started making more solvent, dark energy. This implies the universe eats its own structure to fuel its expansion. A cannibalistic cosmos that consumes its own skeleton to grow its skin. It is a grotesque biological analogy for a sterile physical process. The End of Cosmology is a real paper written by Lawrence Krauss and Robert Scherer. They argue that we live in a very special time, the only time when we can theoretically deduce the true nature of the universe. Before us, it was too hot and dense. After us, it will be too empty and dark. We are the chosen ones of observation. But this privilege comes with a curse, the knowledge of the end. We are the only entities who will ever know that the universe is dying. Ignorance would have been bliss. But we opened the box, and now we have to live with the knowledge of the encroaching dark. There is a chilling quietness to the expansion. It doesn't make a sound. There is no rumble, no tearing noise. It is a silent catastrophe. Galaxies simply drift into the red and fade away. It is the most violent event in history, the tearing apart of space-time, yet it happens with absolute silence. This silence is deceptive. It creates a false sense of security. We look at the night sky and see peace. But if our eyes could see the redshift, we would see a sky screaming in agony as it is stretched beyond its limits. We are deaf to the screams of the cosmos. Think about the God of the gaps. As science explains more, the gaps for mystery shrink. But dark energy and dark matter are not gaps. They are the ocean. 95% of the universe is unknown. We have explained only the foam on top of the waves. We are not closing in on a theory of everything. We are realizing that our theory of everything applies to almost nothing. We are experts on the debris, ignorant of the storm. The more we learn, the more we realize we are strangers in a strange land, surrounded by forces that dwarf our comprehension. Is there a way out? Some speculate about wormholes. If space is stretching, maybe we can punch a hole through it to travel between the receding islands. But wormholes require negative energy to stay open. Ironically, dark energy acts a bit like negative pressure. Could the very thing destroying the universe be used to navigate it? It is a desperate hope. It's like trying to use the water flooding your house to power a boat. Maybe. But more likely, the forces involved are simply too vast for a Type 0 civilization like us to ever harness. We are ants trying to dam a tsunami. The Hubble tension might be a hint that our fundamental assumptions about the universe's geometry are wrong. Maybe the universe isn't flat. The CMB data says it is flat to within 0.4% margin of error. But if it is slightly closed, it could still recollapse. If it is slightly open, the rip is inevitable. We are measuring the curvature of a balloon from the perspective of a bacteria on its surface. We think it's flat because we are small. But the curvature is there, hiding in the decimals, waiting to reveal the true shape of our fate. We have to consider the possibility that the universe is a simulation and the expansion is a memory optimization technique. In a computer simulation, you don't render what isn't being observed. By expanding the universe faster than light, the system ensures that distant regions are never observed, saving processing power. The cosmic event horizon is a rendering distance limit. As the simulation runs longer, the system needs to free up resources, so it decreases the rendering distance, pulling the galaxies away, deleting the complex data of the deep cosmos. We are being optimized out of existence. This leads to the Boltzmann brane paradox. In an eternal expanding vacuum, random quantum fluctuations will eventually create structured matter. Given infinite time, it is more likely that a single human brain, fully formed with false memories of a past, will pop into existence out of the chaos than for a whole universe to evolve naturally. Are you a real person with a history? Or are you a Boltzmann brain that materialized in the void a second ago, hallucinating this video? In a dark energy universe that lasts forever, the freaks eventually outnumber the normal observers. The concept of forever is the most terrifying part of the expansion. Humans cannot grasp eternity. We think in lifetimes, dynasties, maybe geological eras. But the dark energy era will last for 10 to the power of 100 years. That is a number so big that if you wrote a 0 on every atom in the universe, you wouldn't have enough atoms. The era of stars, the era of light and life, is just a brief flash, a camera shutter opening and closing at the beginning of an endless movie of darkness. We are the anomaly. The universe is dead for almost all of its history. We just happen to be alive in the split second it breathes. Every time you look at a star, you are seeing a ghost. The light took millions of years to get here. But now, you are seeing a prisoner. That star is being carried away. The constellations we map are temporary patterns. The Big Dipper will warp and stretch. Eventually, the stars will drift apart so far that constellations will be impossible. Our myths, our zodiacs, our navigation systems, they are all based on a temporary arrangement of fleeing sparks. We are projecting meaning onto an explosion. Physics is the study of symmetries. But dark energy breaks the symmetry. It introduces an arrow of time that points ruthlessly toward nothingness. It suggests that the universe has a telos, a goal, and that goal is emptiness. Why does the universe want to be empty? Why does it spend so much energy clearing the board? It feels like an immune system flushing out a virus. Maybe complex matter is the infection, and dark energy is the fever designed to sterilize the vacuum. We build telescopes like cathedrals to worship the light. But the light is losing. The redshift is the hallmark of our defeat. Every redshifted photon is a loss of energy. The universe is bleeding energy into the expansion. Where does that energy go? In general relativity, energy isn't conserved on cosmic scales. It just disappears. The light gets tired, stretches out, and dies. We are living in a leaking boat, and the ocean is infinite. So, what do we do with this information? We can't stop the expansion. We can't leave the universe. We can only witness it. There is a certain bravery in staring into the abyss and calculating its rate of growth. We are the species that discovered its own expiration date. We looked at the darkness and forced it to give us a number, 73 kilometers per second per megaparsec. It is a small victory, but it is ours. We know the monster's name, even if we can't fight it. But the mystery isn't over. As we peer closer at the data, cracks are appearing in the dark energy theory too. The lambda CDM model fits most things, but not everything. There are small wiggles in the data, tiny inconsistencies in the cosmic web. These might be the keys to a new physics, a physics that saves us from the freeze. Or they might be the cracks in the dam before it bursts. We are walking toward the edge of the map, and the only thing we know for sure is that the ground is moving beneath our feet. While the vast majority of the universe is running away from us in terror, there is one colossal object that is rushing toward us with murderous intent. This is the Andromeda Galaxy, our nearest galactic neighbor, and it is the exception that proves the terrifying rule of dark energy. While the space between galaxy clusters is expanding, the gravity within our local group is still strong enough to overcome the push of the void, for now. Andromeda is hurtling toward the Milky Way at 110 kilometers per second. It is a slow-motion collision that has been destined since the birth of the cosmos. In about 4 billion years, the sky will change. The comfortable band of the Milky Way will be twisted and distorted as a second, larger galaxy crashes into our own, a chaotic dance of gravity that will fling stars into the darkness and ignite a firestorm of new star formation. This merger will create a new, elliptical supergalaxy that astronomers have nicknamed Milkdromeda. It sounds cute, but the reality is a gravitational cage match. While stars themselves rarely collide because the space between them is so vast, the gas clouds will smash together, creating shockwaves of stellar birth and death. Supermassive black holes at the centers of both galaxies will spiral inward, merging in a cataclysmic event that will release more energy than all the stars in the universe combined. But here is the existential twist. By the time this merger settles, the rest of the universe will be gone. The expansion will have pushed all other galaxies beyond the cosmic horizon. The inhabitants of Milkdromeda will look up and see only their own galaxy, surrounded by an infinite, featureless black void. They will be the loneliest civilization in history. This future isolation is so absolute that it threatens the very practice of science. Imagine a scientist in Milkdromeda 100 billion years from now. They point their telescopes at the void and see nothing. No redshift, no other galaxies, no cosmic microwave background, as it has been stretched into unreadable radio waves. They would conclude, logically and scientifically, that the universe is static, eternal, and consists of only one galaxy. They would be wrong. The evidence of the Big Bang and the expansion is temporary. We are living in a fleeting window of transparency. The universe is not just hiding its future from us, it is actively erasing its past. We possess a privileged view that will be denied to all future observers, making us the custodians of a truth that will one day be physically impossible to prove. To understand the mechanism of this erasure, we have to look at the vast empty spaces that act as the engines of expansion, the cosmic voids. Voids are not just empty rooms, they are bubbles of repulsion. The Boots void, often called the Great Nothing, is a region of space 330 million light-years in diameter that contains almost no galaxies. If you were dropped into the center of it, you would see nothing but absolute blackness in every direction. These voids are growing. As matter clumps together due to gravity, the voids between the clumps get emptier. Dark energy is more potent in these empty spaces because there is no gravity to counteract it. The voids are expanding faster than the clusters, squeezing the universe's matter into thin, fragile filaments. We are being pushed into the corners of the room by an inflating balloon of nothingness. It turns out we aren't just being pulled by the great attractor, we are being pushed by a dipole repeller. By mapping the flow of galaxies, scientists discovered a region of space behind us that is pushing the local group away. This region is a void so profound that its lack of gravity acts like a repulsive force relative to the dense regions around it. It creates a cosmic wind that blows us across the universe. We are caught in a gravitational riptide, pulled by the monsters in front of us and pushed by the ghosts behind us. This push-pull dynamic is reshaping the local universe, clearing out the suburbs of the cosmos and packing galaxies into dense urban centers before the final isolation begins. It is a cosmic gentrification where the poor neighborhoods, the voids, are taking over the map. But there is an anomaly in the data that hints at something even stranger than dark energy, the axis of evil. When we look at the cosmic microwave background, the oldest light in the universe, we expect it to be random and uniform. But it isn't. There is a strange alignment in the temperature fluctuations that lines up perfectly with the plane of our solar system. This shouldn't happen. The universe is 13.8 billion years old. Our solar system is only 4.5 billion years old. Why would the echo of the Big Bang care about the orientation of Earth? Some dismiss it as a statistical fluke, a trick of the data processing. But others fear it suggests the Copernican principle is wrong. If the universe is aligned with us, are we in a simulation? Or is the geometry of the universe fundamentally different than we think? This axis of evil points to a potential crisis in our standard model of cosmology. We assume the universe is isotropic and homogeneous, meaning it looks the same in all directions and is made of the same stuff everywhere. This assumption is the bedrock of all our calculations about dark energy. If this assumption is wrong, if the universe has a preferred direction or a lumpy structure, then our deduction that the universe is accelerating might be an optical illusion. We might be mistaking a lopsided universe for an exploding one. It would be the biggest case of mistaken identity in scientific history, transforming dark energy from a mysterious force into a simple error of perspective. But for now, the data holds, and the mystery deepens. Let's dig deeper into the KBC void hypothesis. Some astronomers argue that the Milky Way is situated inside a massive cosmic void, roughly 2 billion light-years across, which is much emptier than the average universe. If we are living in a hole, then the matter outside the hole would pull on the galaxies near the edge, making them move away faster. This would mimic the effects of dark energy without requiring a new mysterious force. It solves the Hubble tension perfectly. Measurements inside the void using supernovae would look different from measurements outside the void using the CMB. It is an elegant solution, but it is terrifying in its own way. It implies we are living in a cosmic backwater, a desolate patch of real estate that distorts our view of the entire universe. But most physicists don't buy the void explanation because of a specific ruler we use to measure the cosmos: baryon acoustic oscillations, BAO. These are sound waves from the early universe that got frozen in time. In the hot plasma of the infant universe, sound waves traveled outward from density spikes. When the universe cooled, these waves stopped, leaving a ring of slightly higher density, a shell of galaxies, at a specific radius. We can see these rings in the sky today. They act as a standard ruler of a known length, about 500 million light-years. By measuring how big these rulers look at different distances, we can map the expansion history of the universe independent of supernovae. And the scary thing? The BAO data confirms the acceleration. The ruler is stretching. The expansion is real, not an illusion of our location. This confirmation brings us back to the vacuum catastrophe. If the expansion is real, the energy of space is real. We are swimming in a sea of zero-point energy. According to quantum mechanics, you can never remove all energy from a system. There is always a jitter, a fluctuation. If you could tap into this zero-point energy, you would have infinite power. It is the holy grail of science fiction, zero-point modules, warp drives. But the universe seems to have a firewall. Whenever we try to interact with the vacuum energy, we find it is inaccessible. It pushes galaxies apart, but it refuses to turn on a light bulb. It is a force that acts on the scale of gigaparsecs, ignoring the petty needs of biological creatures. There is a nightmare scenario involving this vacuum energy called vacuum decay. We mentioned it briefly, but the mechanics are pure horror. The Higgs field, which gives particles their mass, might not be stable. It might be in a metastable state, like a pencil balanced on its tip. All it takes is a quantum tunnel event, a push, to knock it over into a lower energy state. If this happens, a bubble of true vacuum will nucleate. Inside this bubble, the laws of physics change. Constants shift. Chemistry becomes impossible. This bubble expands at the speed of light. You would never see it coming, because it moves as fast as the light that would warn you. One instant you are there, the next, you are simply disassembled into raw energy. Dark energy might actually be the solution to the Fermi paradox, the question of where is everybody? If civilizations arise billions of years apart, the expansion of the universe ensures they never meet. By the time a civilization becomes advanced enough to attempt intergalactic travel, their neighbors have already receded beyond the horizon. The universe isolates intelligence. It quarantines life. We might be alone not because life is rare, but because the universe is designed to keep us apart. It is a cosmic form of social distancing that lasts for eternity. The silence of the night sky is not empty. It is deafening evidence of a universe that forbids connection. Let's talk about the geometry of the universe again. We say it is flat, but what does that mean? In a flat universe, parallel lines never meet, and triangles have angles that add up to 180 degrees. If the universe is truly flat, and dark energy is a constant, then the universe must be infinite in extent. An infinite universe leads to a breakdown of identity. In an infinite space, particle arrangements must eventually repeat. There are only so many ways to arrange atoms. If you go far enough, about 10 to the power of 10 to the power of 28 meters, you will find an exact copy of yourself reading the script. In an accelerating, infinite universe, there are infinite versions of you, living every possible variation of your life, all isolated from each other by the expanding dark. But maybe dark energy isn't a constant. Maybe it's a dynamic field called quintessence. Unlike the cosmological constant, quintessence can evolve. It can thaw or freeze. In a thawing model, dark energy was frozen in the early universe and is now waking up, becoming more powerful. In a freezing model, it is slowly dying out. If it dies out, the expansion could stop. Gravity could take over again, leading to a big crunch. But current data from the Dark Energy Survey suggests it is staying remarkably constant, or perhaps getting slightly stronger. The universe seems to prefer the path of destruction over the path of collapse. It chooses the cold death over the fiery one. Recent news from the DESI, Dark Energy Spectroscopic Instrument Collaboration, has sent shockwaves through the physics community. Their preliminary data hints that dark energy might not be constant. It might be weakening slightly as time goes on. This is huge. If dark energy is weakening, the Big Rip is canceled. The heat death might be postponed. It opens the door for a universe that is more complex and dynamic than the static death march we feared. But weakening doesn't mean stopping. It just means the accelerator is being pressed slightly less hard. We are still speeding toward the cliff, just a little slower than we thought yesterday. Or perhaps gravity is leaking. String theory proposes that our universe is a brane, a 3D slice of a higher dimensional bulk. Gravity is unique among the forces because it is so weak. A tiny magnet can lift a paperclip against the gravitational pull of the entire Earth. Why is gravity so weak? Maybe it isn't. Maybe gravity is just as strong as the other forces, but it leaks out of our dimensions into the bulk. If gravity leaks, it weakens over distance faster than it should. On cosmic scales, this leakage could look like an acceleration. We might be interpreting a higher dimensional leak as a repulsive force. We are seeing the shadows of a fifth dimension and calling it dark energy. Think about the ohm diagnostic, a mathematical tool used to distinguish between different dark energy models. It compares the expansion rate at different redshifts. If the universe follows the standard model, lambda CDM, the ohm value should be constant, but some recent studies show it fluctuating. This is the crack in the dam we spoke of. These fluctuations suggest that our smooth, elegant equations are failing to capture the jagged reality of the cosmos. The universe is messy. It glitches. And in those glitches, we might find the truth that saves us, or the truth that confirms our worst fears. What if the universe is not expanding, but the mass of particles is changing? This is a controversial idea proposed by some theoretical physicists. If all atoms are slowly getting heavier over time, the light they emit would shift toward the red. This would look exactly like an expansion, but in reality, the universe is static. We are just shrinking or changing internally. It would mean the expansion is an illusion of relativity. The universe isn't growing, we are just changing our scale. It feels like a desperate attempt to save the static universe, but in quantum mechanics, mass and energy are interchangeable. A changing mass field is indistinguishable from an expanding space. Let's return to the supernovae. We use them as standard candles because we think they all explode at the same brightness. But what if they don't? What if supernovae in the early universe were chemically different? Younger stars have fewer heavy elements, metals. If metal-poor stars explode fainter than metal-rich stars, we might be miscalculating the distances. We might be overestimating the expansion. This evolutionary effect is the biggest skepticism against dark energy. Maybe the universe isn't accelerating. Maybe we just don't understand how stars explode. We are basing the fate of the cosmos on the assumption that a bomb detonates the same way today as it did 10 billion years ago. Despite these doubts, the consensus remains strong because of the cosmic concordance. Different independent methods, supernovae, CMB, BAO, and gravitational lensing, all point to a universe that is about 70% dark energy. It is highly unlikely that 4 completely different methods would all be wrong in the exact same way to produce the exact same illusion. The conspiracy of nature would have to be incredibly elaborate. It is far more likely that the monster is real. We are cross-referencing the fingerprints, the DNA, and the eyewitness testimony, and they all point to the same suspect. The vacuum itself is the killer. Gravitational lensing provides a direct way to weigh the darkness. When light from a distant galaxy passes a massive object, it bends. By measuring this bending, we can map the distribution of dark matter. But recently, we have started looking at weak lensing, the subtle distortion of millions of galaxies. The results from the Dark Energy Survey show that the universe is slightly less clumpy than Planck predicted. The web of matter is smoother than it should be. This smoothness suggests that dark energy is pushing apart the clumps, smoothing out the structure of the universe like a rolling pin flattening dough. It is actively fighting against the formation of structure. This S8 tension, the clumpiness problem, is the little sibling of the Hubble tension. Both tensions point in the same direction. The late universe is behaving differently than the early universe. It is as if the laws of physics matured or shifted as the cosmos aged. This has led to theories of variable constants. Maybe the speed of light wasn't always the speed of light. Maybe the gravitational constant, g, has changed. If the fundamental constants are not constant, then our entire history of the universe is a fiction based on a false premise. We are building a house on quicksand. Imagine the universe as a black hole. There is a theory that our universe is the interior of a black hole in a 4D universe. When a 4D star collapses, it forms a 3D event horizon. We are the 3D skin of that 4D implosion. In this model, the expansion we see is actually the growth of the black hole as it swallows more 4D matter. We are the debris of a higher dimensional meal. It explains the Big Bang, the moment of collapse, and the expansion, the growth of mass. We are living inside the monster, mistaking its digestion for our history. The holographic principle adds another layer of surrealism. It suggests that all the information in our 3D universe is actually encoded on a 2D surface at the boundary of the cosmos. We are 3D holograms projected from a 2D reality. If dark energy is expanding the boundary, it is increasing the pixels available for the universe. But if the acceleration continues, the information density drops. The projection gets stretched. Are we becoming a lower resolution version of ourselves? Is the universe running out of bandwidth? Let's look at the lithium problem. The Big Bang Theory predicts exact amounts of hydrogen, helium, and lithium. We get the hydrogen and helium right, but we find only 1/3 of the predicted lithium. Where did it go? Did it decay? Or did new physics in the early universe destroy it? This missing lithium is a nagging reminder that we don't understand the first few minutes of creation. If we can't balance the checkbook for the first 3 minutes, why do we trust our predictions for the next 100 billion years? Neutrinos might hold a clue. These ghost particles pass through Earth by the trillions every second. We discovered they have mass, which was a shock. Now we wonder if the cosmic neutrino background plays a role in dark energy. If neutrinos interact with a scalar field, they might be the trigger that switched on the acceleration. The mass-varying neutrino theory suggests that as neutrinos slowed down, they transferred energy to the vacuum, kickstarting the expansion. The smallest, most ghostly particles might be responsible for the largest motion in history. We are building this square-kilometer array, a radio telescope network that will map 1 billion galaxies. It will be the ultimate eye on the sky. We hope it will reveal the wiggles in the distribution of matter that prove or disprove dark energy theories. But there is a fear that better data will just bring more confusion. In cosmology, precision often leads to paradox. The sharper the image, the less it makes sense. We might find that the universe is fractal, that the expansion is chaotic, and that there is no single number that describes our fate. What about the great filter again? If civilizations are common, maybe they destroy themselves by experimenting with high-energy physics. Experiments to probe dark energy or create baby universes might be catastrophic. Some physicists have warned that particle accelerators could theoretically trigger vacuum decay. While the risk is infinitesimally small, the consequence is infinitely bad. Are we the toddler playing with a loaded gun, trying to understand the bullet by hitting it with a hammer? The silence of the universe might be the graveyard of those who pushed the button. Let's consider the psychological impact of the end of the universe. For millennia, humans believed in cyclical time or eternal heavens. Dark energy forces us to confront linear, finite time. It imposes a narrative structure: beginning, middle, end. And the end is a whimper, not a bang. It robs us of the hope for legacy. If the universe eventually erases all traces of existence, then nothing we do matters on a cosmic scale. Shakespeare, Einstein, the pyramids, all will be deleted. Dark energy is the ultimate nihilist. It is the scientific proof of Ozymandias. Look on my works, ye mighty, and despair. But there is a rebellion against this nihilism. Freeman Dyson proposed eternal intelligence. He argued that if a civilization hibernates, processing information only when the temperature drops, it can stretch its subjective time to infinity. Even in a freezing universe, thought can continue. By slowing down, by becoming colder and slower, life can cheat the heat death. We might evolve into clouds of super-cold gas, thinking one thought every billion years, but thinking forever. We can survive the dark by becoming the dark. This assumes the Big Rip doesn't happen. If the rip happens, there is no hibernation. The structure of thought itself is torn apart. This is why the value of W matters so much. If W equals -1, we can sleep and dream forever. If W less than -1, we are executed. The difference is in the decimal points. We are waiting for the judge to read the verdict, and the trial is taking place in the data centers of the European Space Agency. Let's look at the dark siren gravitational waves. When black holes collide, they ripple space-time. These ripples are standard sirens. They tell us the distance directly without needing messy stars. As LIGO and Virgo detect more crashes, we are building a third independent measurement of the Hubble constant. Early results are ambiguous. They sit right in the middle of the tension. The universe is refusing to take a side. It is keeping us in suspense, playing both sides of the paradox against each other. There is a concept called cosmic variance. It means that because we only have one universe to look at, we can't run statistics properly. We have a sample size of one. We can't compare our universe to others to see what is normal. Maybe our universe is a freak outlier. Maybe in most universes, dark energy is zero. We are trying to derive the laws of all nature from a single, possibly flawed specimen. It is like trying to understand human psychology by studying only one person who has been in solitary confinement for 40 years. We often speak of the observable universe, but the unobservable universe is likely infinite. Inflation theory suggests the universe expanded faster than light in the first fraction of a second, creating a cosmos much, much larger than what we see. If this is true, then the dark energy we see might just be a local fluctuation in a much larger, more complex landscape. We are seeing the weather in our backyard and assuming it's the climate of the planet. We are arrogant in our extrapolation. One of the strangest solutions to the dark energy problem is that time is slowing down. If time itself were decelerating, it would look like the universe is accelerating away. When we look at distant galaxies, we are looking into the past. If time flowed faster back then, the light would arrive differently. In this theory, the universe ends not by ripping, but by freezing in time. Everything stops. The now becomes an eternal instant. It is a snapshot that never fades, a movie that pauses on the last frame forever. The inflaton field that caused the Big Bang and the dark energy field causing the expansion might be related. Some theories suggest dark energy is just the remnant of the inflation field that didn't quite turn off. It's the embers of the Big Bang still glowing. If this is true, it connects the beginning and the end in a poetic loop. The force that birthed us is the force that will kill us. The creator and the destroyer are the same entity. We have to mention the antimatter problem. We shouldn't be here. The Big Bang should have created equal parts matter and antimatter, which would have annihilated each other instantly. But for some reason, matter won. A tiny imbalance allowed us to exist. Is dark energy related to this imbalance? Is it the cost of our existence? Maybe the energy required to save matter from annihilation had to come from somewhere, and the debt is being paid now in the form of expansion. The universe is rebalancing the books. What if dark energy is an interaction with shadow matter? Matter that only interacts via gravity and the scalar field. This shadow sector could be as complex as our own. With shadow stars and shadow planets, we would pass right through them. But their energy would push space apart. We might be sharing our universe with a ghost reality that is crowding us out. The expansion is just the pressure of two universes trying to occupy the same space-time. The philosophical horror of the expansion is that it turns the universe into a prison of solitary confinement. In the far future, no signal can ever leave the local group. No signal can enter. We will be causally disconnected from the rest of existence. It is the ultimate quarantine. If there is a galactic internet, the nodes are going offline one by one. The silence we hear is the sound of connections snapping. And yet, we continue to launch telescopes. We continue to calculate. Why? Because we are the universe attempting to understand itself. Even if the answer is death, the act of knowing is defiance. We are looking the executioner in the eye. The expansion is faster than light, but the human mind is expanding too, trying to encompass the void before the lights go out. We are racing the darkness. But let's not get too heroic. The numbers don't care about our defiance. The cosmological constant is 10 to the power of minus 52 per square meter. It is a tiny, tiny number, but it is relentless. It never sleeps. It never stops. It accumulates. It is the compound interest of doom. Over billions of years, that tiny number becomes the only number that matters. It swallows galaxies whole. It is the tortoise that beats the hair of gravity. Some scientists propose we build stellar engines, Shkadov thrusters, to move our solar system. Could we pilot our star toward other galaxies to keep them within our horizon? Could we build a cluster arc to preserve a community of galaxies against the expansion? It is a project for a Type 3 civilization. But even moving at near light speed, we are fighting the fabric of space itself. We would be trying to outrun the treadmill. The dark forest theory of the cosmos usually refers to hostile aliens. But the true dark forest is the expansion. The trees are moving away. The paths are disappearing. We are not hiding. We are being lost. The forest is becoming a desert. And in a desert, you don't need predators to kill you, you just need time and isolation. The universe is not a battlefield. It is a waiting room for extinction. Let's reconsider the big crunch. If dark energy is actually a field that oscillates, it could switch from repulsive to attractive, it could pull the universe back together. This leads to the big bounce, a universe that expands, stops, crunches, and bangs again. An eternal heartbeat. But the entropy problem remains. Each bounce would get messier. Eventually, the bounces stop. Even in a cyclic universe, there is an end. There is no true eternity in physics. The arrow of time is defined by entropy disorder increases. The expansion of the universe allows entropy to increase forever. If the universe stopped expanding, entropy might max out, and time would stop. The expansion is the fuel that keeps time moving. We are aging because the universe is growing. Our mortality is linked to the redshift. We die because the universe refuses to sit still. What if we are wrong about the redshift? This is the tired light hypothesis. It was discarded decades ago, but it keeps coming back in fringe theories. If light simply loses energy as it travels, the universe isn't expanding. It's static. It's safe. But tired light fails to explain the time dilation of supernovae. We see distant explosions happening in slow motion. Only expansion explains that. The universe is not just making light tired, it is stretching the seconds themselves. The cosmological principle says we aren't special, but the anthropic principle says we must be special to exist. Dark energy sits at the intersection of these two. It is fine-tuned to allow us, but it is ruthless in destroying the conditions for us. It is a universe that invites guests in, gives them a brief party, and then burns down the house. It is a hospitable trap. We have mapped the Laniakea supercluster, our home. It contains 100,000 galaxies. It looks like a giant feather of light. But even Laniakea is being torn apart. Dark energy is dissolving the feather. The tip is moving away from the stem. We are losing our hometown. We are not just citizens of Earth. We are citizens of a dissolving state. The Great Wall, the Sloan Great Wall. These massive structures are the largest things in the universe. They are over 1 billion light-years long, but they are the limit. Dark energy prevents anything larger from forming. It has put a cap on the size of reality. It says, this big and no bigger. It is the glass ceiling of the cosmos. As we reach the midpoint of our investigation, the picture is clear. The universe is a machine designed to create isolation. It is an engine of loneliness. We are small, we are temporary, and we are moving apart. But the story isn't over. There are still theories that offer a twist, strange possibilities hiding in the quantum foam that might rewrite the ending. We have to go deeper into the impossible. To truly grasp the absurdity of our situation, we must look at the cosmological constant problem in its raw, mathematical horror. Quantum field theory, the most successful theory in human history, predicts that the vacuum of space should be dense with energy. It predicts a value for the energy density of the vacuum that is enormous, a number that would instantly curl the universe into a microscopic ball or rip it into subatomic shreds. But when we look at the universe, the actual energy density driving the expansion is incredibly small, 120 orders of magnitude smaller than the prediction. This is not just a rounding error. It is like guessing the weight of the entire universe and missing by a factor of everything. It implies that there is some mechanism canceling out almost all of that energy, leaving just a tiny sliver behind. That tiny sliver is what we call dark energy. We exist in the rounding error of a cancellation we do not understand. This leads us to the coincidence problem. Why now? Throughout the history of the universe, the ratio of matter to dark energy has changed wildly. In the early universe, matter and radiation dominated. In the far future, dark energy will dominate completely. We just happen to live in the brief, fleeting epoch where they are roughly comparable, roughly 30% matter and 70% dark energy. It feels suspicious. Why would intelligent life evolve exactly at the moment when the universe is transitioning from a gravity-dominated deceleration to a vacuum-dominated acceleration? Are we observing this transition because it is required for our existence? Or is it a temporal trap? It suggests that our existence is inextricably linked to this precise balance, and as the balance tips, our time may be running out. One proposed solution to the coincidence problem is quintessence. Unlike the rigid cosmological constant, quintessence is a dynamic field that changes over time. It is a tracker field, meaning it mimics the energy density of the dominant component of the universe. When radiation dominated, quintessence followed it. When matter dominated, it followed that. But now, it has frozen and taken over. If quintessence is real, it offers a glimmer of hope, or a new kind of terror. Because it is dynamic, it could change again. It could decay into radiation, heating the universe back up. Or it could turn negative, causing a sudden collapse. It turns the solid ground of spacetime into a shifting sand dune that could swallow us at any moment. But what if gravity itself is the liar? We base all our calculations on general relativity, which works perfectly inside our solar system. But what if gravity behaves differently when the gravitational acceleration is incredibly low, like in the outskirts of galaxies or the deep void? This is the premise of MOND, modified Newtonian dynamics. If gravity falls off more slowly than we think, we wouldn't need dark matter to hold galaxies together. However, MOND struggles to explain the expansion of the universe itself. To fix MOND to explain dark energy, you have to twist it into knots, creating theories like TeVe's, tensor vector scalar gravity. These theories are Frankenstein monsters of math, stitched together to avoid admitting that the universe is filled with invisible ghosts. The chameleon field is one of the most fascinating attempts to explain why we can't detect dark energy in the lab. A chameleon particle has a variable mass that depends on the density of its environment. Here on Earth, where the air is dense, the particle becomes extremely heavy and interacts only over microscopic distances, making it invisible to our experiments. But in the vacuum of space, where density is low, the particle becomes light and its range extends across the cosmos, creating the repulsive force we see as dark energy. It is a force that hides in the shadows of matter. It suggests that the laws of physics are not the same in a room as they are in the void. We are trying to study a ghost that disappears the moment we turn on the lights. Let's project the timeline forward to the era of isolation. In about 100 billion years, the local group will have merged into one galaxy, and all others will have vanished. But the expansion continues. Eventually, the expansion of space will happen faster than the orbital speed of planets. This is the unbinding. First, the galaxy dissolves. Stars drift away from the core. Then, solar systems dissolve. Planets drift away from their stars into the cold dark. Finally, the atoms themselves are pulled apart. But before the Big Rip, there is the Big Freeze. In this scenario, stars simply run out of fuel. The universe becomes a graveyard of black holes, neutron stars, and cooling white dwarfs. The lights go out, one by one, until the cosmos is a vast, cold tomb. In the black hole era, which begins roughly 10 to the power of 40 years from now, the only dynamic objects left are black holes. They will wander the darkness, occasionally merging but mostly just evaporating via Hawking radiation. This process is agonizingly slow. A supermassive black hole takes googles of years to evaporate. During this time, the universe is effectively dead. It is a dark room with a few dying embers. If any consciousness survives, it will be huddled around the event horizons, harvesting the last trickles of thermal energy from the decay of gravity monsters. It is a scavenging existence, feeding on the corpse of the universe. But it gets worse. If protons are unstable, as many grand unified theories predict, then ordinary matter cannot last forever. Protons will eventually decay into positrons and pions, which then decay into gamma rays. This means that planets, dead stars, and even the dust of the universe will dissolve into radiation. The proton decay era means that physical structure is temporary. You, the chair you sit on, the Earth, we are all just temporary knots in a field that wants to untie itself. Eventually, there will be no matter left to define a place. The universe will be a soup of photons and leptons, stretching forever into a meaningless void. If protons don't decay, we face the iron star scenario. Over incredibly vast timescales, quantum tunneling allows atoms to fuse even at absolute zero. Slowly, very slowly, all ordinary matter will transmute into iron-56, the most stable isotope. Stars that didn't explode will turn into cold spheres of solid iron. The universe will be filled with rusting, frozen cannonballs floating in the dark. But even these iron stars aren't safe. Given enough time, 10^10 to the power of 76 years, quantum tunneling will cause these iron stars to collapse into neutron stars or black holes, which will then evaporate. The end result is the same: nothingness. The universe is efficient. It cleans up its mess eventually. There is a concept called the thermodynamic arrow of time. We perceive time flowing forward because entropy disorder increases. But in a universe that has reached heat death maximum entropy, there is no forward anymore. Time effectively stops. However, in a universe with a cosmological constant, there is always a temperature, the Gibbons-Hawking temperature of the horizon. This means there are always thermal fluctuations. In an infinite amount of time, these fluctuations can randomly assemble into low entropy states. This brings us back to the Boltzmann brain. In the eternity of the heat death, the universe will dream momentary existences. It will hallucinate worlds that exist for a nanosecond and then dissolve. The afterlife of the universe is a chaotic nightmare of random data. Let's look at the dark flow again. In 2008, astronomers found that galaxy clusters are moving at 600 kilometers per second towards a patch of sky between Centaurus and Hydra. This motion is distinct from the expansion. It implies a massive gravitational pull from outside the observable universe. This could be the imprint of a neighboring universe in the multiverse pressing against ours, or a remnant of the inflationary epoch, a tilt in the fabric of space-time. Whatever it is, it drags us. We are like leaves in a stream, drifting towards a waterfall we cannot see. The expansion pushes us apart, but the flow drags us together towards a mystery beyond the horizon. The cold spot in the cosmic microwave background is another scar on the face of reality. It is a region of the sky that is significantly colder and larger than expected. The standard model says it shouldn't exist. The odds are less than 1%. Some physicists, like Roger Penrose, argue it is evidence of a past universe, a Hawking point where a black hole from a previous eon evaporated. Others suggest it is the bruise left by a collision with another bubble universe. Imagine two soap bubbles touching. The point of contact would look different. If this is true, we have physical evidence that we are not alone in the multiverse, and that our bubble is fragile. What if dark energy is related to the holographic principle? If the 3D universe is a projection of 2D information on the cosmic horizon, then the surface area of the horizon determines how much information the universe can hold. As the universe expands, the horizon area grows, allowing more information, entropy. But the density of information decreases. This suggests that the resolution of reality is dropping. In the early universe, physics was high definition. In the far future, it will be blocky and pixelated. We might be experiencing quantization noise, the static of a simulation running out of bit depth. The expansion is the result of the system trying to accommodate more data by stretching the screen. We must consider the doomsday argument, a probabilistic theory that suggests we are likely living in the middle of human history, not the beginning. If humanity were to span the galaxy and live for billions of years, the total number of humans would be trillions. The odds of you being one of the first few billion, us now, would be infinitesimally small. It is statistically more likely that humanity will go extinct soon, capping the total number of humans. The expansion of the universe plays into this. By isolating us, it prevents the colonization of the cosmos, keeping the population number low. The universe's geometry enforces the doomsday argument. It ensures we remain a small, finite footnote in history. Eternal inflation is a theory that says the Big Bang wasn't a one-time event. Instead, space is always inflating at a high rate, and occasionally, a bubble stops inflating and turns into a universe like ours. This means the greater multiverse is a frothing ocean of exponential expansion, and our universe is just a tiny, calm bubble within it. But the space between bubbles is expanding faster than light. We can never reach another bubble. We are castaways on an island in an ocean that grows forever. The other islands are there, perhaps with other laws of physics, other lives, but they are forever beyond our reach. The multiverse is a crowded place where no one can ever meet. The measure problem in cosmology asks, how do you calculate probabilities in an infinite multiverse? If everything that can happen does happen an infinite number of times, then how can we say anything is likely or unlikely? Dark energy complicates this. It puts a time limit on observation in our bubble. It suggests that observable universes are rare. Most of the multiverse is empty, expanding void. We are in a habitable zone of probability. But this zone is shrinking. As the expansion accelerates, the fraction of the universe that supports life drops towards zero. We are the 1% of the 1% of the 1%. Let's talk about the redshift drift. This is a measurement we haven't made yet, but we will. If we watch a distant galaxy for a decade, its redshift should change by a tiny amount due to the acceleration. This is the Sandage-Loeb test. It would be the first real-time movie of the expansion. Currently, we only have snapshots. Seeing the drift would be like watching the bomb timer count down. It would turn cosmology from archaeology into meteorology. We would be forecasting the weather of the apocalypse. The Extremely Large Telescope, ELT, being built in Chile, aims to detect this. We are building the eyes to watch our own demise. There is a theory called entropic gravity, proposed by Eric Verlinde. It suggests that gravity isn't a fundamental force at all, but an emergent phenomenon of entropy, like heat. In this view, dark energy is also an emergent effect, a result of the information content of space changing. If gravity is just a side effect of thermodynamics, then the expansion of the universe is just the system trying to maximize its entropy. We are being pushed apart not by a mysterious energy, but by the statistical inevitability of disorder. The universe isn't exploding. It's just getting messy on a cosmic scale. Scalar tensor vector gravity, STVG, is another modification theory. It proposes a fifth force that acts differently on different scales. This force could explain the acceleration without dark energy, but introducing a fifth force opens a Pandora's box. If there is a fifth force, why haven't we seen it in the lab? It implies that our experiments are blind to a fundamental aspect of reality. We are like 2D creatures trying to understand a 3D sphere passing through our plane. We see a growing circle, expansion, but we can't see the sphere, the fifth force. The void phenomenon suggests that we live in the largest void in the observable universe, the KBC void. If we are in a region of low density, matter flows out of the void toward the denser edges. This outflow mimics acceleration. It would mean the expansion is just a local traffic jam of galaxies leaving our neighborhood. But for the void to be big enough to fool us, it would violate the Copernican principle. It would mean we are in a special, uniquely empty place. Why are we here? Maybe because life can't survive in the dense, radiation-filled regions. The void is our oasis, but it is also a hall of mirrors distorting our view. Let's consider the Hubble bubble. This is a sharp boundary where the expansion rate changes. If we are inside a bubble with a higher Hubble constant, and the outside has a lower one, it creates tension in the data. But boundaries in space are usually violent. A domain wall between two vacuum states would contain immense energy. If we are in a bubble, what happens when the wall hits us? Or are we the ones expanding into the slow universe, eating it alive? The Hubble bubble turns cosmology into a territorial war between different regions of physics. The early dark energy model suggests a pulse of expansion happened before the recombination era, 380,000 years after Big Bang. This pulse would change the size of the sound horizon, the ruler we use for BAO. If the ruler is shorter than we thought, the universe is expanding faster than we thought. It fixes the Hubble tension. But why did dark energy turn on, turn off, and then turn on again billions of years later? It acts like a dormant virus that flares up periodically. Is there a cycle of dark pulses? If so, another pulse could happen tomorrow, instantly ripping the galaxy apart. Interacting dark energy is the idea that dark energy feeds on dark matter. As dark matter decays, it turns into vacuum energy. This explains why the acceleration started recently. The dark matter had to decay enough to become significant. But this implies the universe is cannibalizing its own skeleton. The gravity that holds galaxies together is rotting away, turning into the force that pushes them apart. It is a self-destruct mechanism built into the architecture of the cosmos. Eventually, there will be no dark matter left, only pure, unadulterated expansion. What about the shape of the universe? The data says it is flat. But a torus, donut shape, is also geometrically flat. In a torus universe, if you look far enough, you see the back of your own head. But dark energy prevents this. The expansion pushes the loop point away faster than light. Even if the universe is a loop, the expansion has severed the connection. We are trapped on a treadmill that is unrolling faster than we can run a lap. The topology doesn't matter if the geometry is expanding. The axis of evil alignment of the CMB with our solar system suggests a small universe. If the universe is finite and small, the long wavelengths of the CMB can't fit. They get cut off. This matches the data. We see a lack of large-scale correlations. But a small universe shouldn't be accelerating this fast. It is a contradiction. Unless the universe is a hypersphere that is inflating, we are ants on a balloon that is being blown up by a giant. The smallness is an illusion of the curvature we can't see. Let's talk about fast radio bursts, FRBs. These are millisecond flashes of energy from deep space. We use them to measure the matter between galaxies, the dispersion measure. They confirm the universe is missing baryons, normal matter. Half the normal matter in the universe is hiding in the warm, hot intergalactic medium. Quote, "The expansion is spreading this matter so thin it is almost undetectable. We are losing track of the protons. The universe is diluting its ingredients to the point of homeopathy." The Kardashev scale ranks civilizations by energy use. Type 3 uses a whole galaxy. But in an accelerating universe, a Type 3 civilization is doomed. They can't hold the galaxy together. The stars at the edge will drift away. A galactic empire is physically impossible to maintain over cosmic timescales because the territory keeps expanding. The limits to growth aren't economic. They are cosmological. Dark energy imposes a hard cap on the ambition of any sentient species. We can never conquer the stars. We can only visit them before they leave. Dyson spheres, stars wrapped in solar panels, might be the only refuge. In the dark era, civilizations will huddle around white dwarfs and black holes, building shells to keep the heat in. The universe will consist of isolated points of light, lonely fortresses in the dark. Communication between them will be impossible. Each sphere will be its own universe, its own history, its own reality. The internet of the cosmos will shatter into billions of disconnected intranets. Could we escape to a parallel universe? The brain world scenario suggests other universes are millimeters away in a fourth spatial dimension. If our universe is dying, could we tunnel to a younger, contracting brain? It is the ultimate sci-fi dream. But gravity is the only thing that leaks between brains. We would have to convert ourselves into gravitational waves to cross the void. We would have to become ghosts to survive the death of our machine. The timescape cosmology theory argues that we are mistaking time dilation for acceleration. In voids, time flows faster. In clusters, it flows slower. Since we look through voids to see distant galaxies, we are seeing a, quote, time mirage. If this is true, dark energy is an artifact of averaging the clock rates of the universe. There is no repulsive force, just a universe where time is out of sync. We are not speeding up. We are just aging at different rates than the void. It is a relativity nightmare where now means nothing. Let's face the vacuum metastability again. If the vacuum decays, the bubble wall moves at light speed. But because space is expanding, could the expansion save us? If space expands faster than light, could we outrun the vacuum bubble? No. The bubble expands into the space. But if the expansion creates a horizon, the bubble might be contained within its own horizon. Parts of the universe could be destroyed while others remain safe, forever unaware of the catastrophe. The universe could be Swiss cheese, full of holes where physics has collapsed, and we wouldn't know until we fell in. The Sloan Digital Sky Survey mapped the universe and found the Great Wall. But it also found the edges of the Webb are fraying. The filaments are thinning. The structure of the universe is dissolving. Gravity builds structure. Dark energy destroys it. We are past the peak of structure formation. The universe was most complex, about 8 billion years ago. Since then, it has been degrading. We missed the party. We are walking through the ruins of the golden age of the cosmos. What if dark fluid is a single substance that acts as dark matter when it flows, and dark energy when it sits still? This unifies the two mysteries, but it implies space is filled with a weird, non-Newtonian fluid. We are swimming in molasses that pushes back when we stop moving. It changes our understanding of motion. We are not moving through empty space. We are moving through a medium that reacts to us. The universe is a reactive substance. The cosmic number hair theorem states that all expanding universes eventually look the same, empty de Sitter space. Dark energy irons out all the wrinkles. It erases the hair, the galaxies, the clusters, the details. It wants a smooth, bald universe. It is an entropy machine designed to remove complexity. We are the wrinkles it is trying to iron out. Life is a resistance against the smoothing function of the cosmos. In the far future, the CMB will redshift until its wavelength is larger than the universe. It will become undetectable. The sky will be truly black. Future civilizations will not have the baby picture of the universe. They will have no way to know about the Big Bang. They will invent theories of a steady-state universe, because that is all the data will support. We are the keepers of the origin story. If we die, the memory of the Big Bang dies with us. We are transmitting signals into space, radio, TV, radar. These signals form a sphere of information expanding at light speed, but the expansion of the universe stretches these signals. Eventually, our I Love Lucy episodes will be stretched into static. Our cultural footprint is being erased by the redshift. We are shouting into a canyon that gets wider every second, making our echo quieter and quieter until it is gone. Gravastars are a theoretical alternative to black holes, bubbles of dark energy held together by a shell of matter. If black holes are actually gravastars, then the universe is full of dark energy bubbles. Maybe the expansion is just these bubbles leaking. Maybe the universe is a foam of gravastars. It connects the smallest monsters, black holes, to the largest monster, expansion. It suggests a fractal danger. The phantom divide is the line where W equals -1. Crossing it means the big rip. Current data puts W at -1.03 plus or minus 0.03. That is terrifyingly close to the edge. We are driving a car at 200 miles per hour, inches from the guardrail. One wrong measurement, one new decimal point, and the theory shifts from lonely freeze to violent shredding. The fate of every atom hangs on a decimal point. Let's talk about cosmic amnesia. If the universe erases its history, is it a cyclical reset? Does the universe want to forget? In the cyclic models, the entropy has to be reset. Maybe the rip is the reset button. It shreds the messiness of the old universe to make way for the new, pristine vacuum. Destruction is a necessary step for rebirth. We are the mess that needs to be cleaned up. Modified gravity theories often use screening mechanisms to hide the extra force in the solar system. The Weinstein mechanism hides the force near heavy objects. This means gravity is deceptive. It wears a mask when we look at it closely and only reveals its true face in the dark. We are studying a trickster force. The local hole is another name for the KBC void. If we are in a hole, we are the underdogs of the universe. We are in the sparse, rural outback. The cities of the universe, the superclusters, are far away and receding. We are stuck in the countryside of the cosmos, watching the lights of the city fade away. Dark energy is a placeholder name. It stands for we don't know. It is the here be dragons on the map, but the dragons are eating the map. Every year, the map gets larger, but the known territory gets smaller relative to the whole. We are losing the epistemological war. Ignorance is growing faster than knowledge. Supervoids, like the Eridanus supervoid, the cold spot, are growing. They will eventually merge. The universe will become one giant void with isolated islands of matter. The Swiss cheese model will turn into just air. The cheese is being eaten. The Hubble tension might be due to a mirror world sector of particles. Dark matter interacting with mirror photons. It sounds like fantasy, but the math works. If there is a mirror universe occupying the same space, does it have mirror life? Are they wondering why their universe is expanding too? Are we pushing against each other? Cosmic shear measures the distortion of galaxy shapes. The results show the universe is flatter and smoother than we thought. The clumpiness parameter S8 is low. This smoothness is the signature of dark energy. It is the ironing board of the gods. It hates texture. It wants a flat, dead sheet. We rely on standard candles, supernovae. But what if they are standard sirens, gravity waves? The sirens are singing a different song. The clash between light and gravity data is the cacophony of a breaking paradigm. We are listening to two different radio stations, playing different songs, trying to mash them into one reality. The look-back time to the edge of the universe is 13.8 billion years, but the co-moving distance is 46 billion light-years. The universe is bigger than its age. This paradox is only possible because of expansion. We are seeing things that are now impossibly far away. We are looking at ghosts that have already left the building. In the end, dark energy is the ultimate memento mori. It reminds us that permanence is an illusion. The stars are not fixed. The ground is not stable. The sky is not eternal. We are travelers on a disintegrating raft. The only thing we can do is chart the course of the wreckage. We are sending golden records on Voyager, hoping someone finds them. But in a dark energy universe, the Voyager probes will eventually be isolated in their own horizon bubbles. They will never be found. They are messages in bottles thrown into an ocean that expands faster than the bottle can float. Our legacy is silence. But there is a dark beauty in this isolation. If we are truly alone, if the universe is separating us from the others, then we are the stewards of this pocket of reality. We are the guardians of the Milky Way. In a dying universe, the only meaning is the one we create before the lights go out. We are the torchbearers in the final night,